Welcome everyone to GeoHug. So before we kick off today's session, I'd just like to take this time to acknowledge the traditional lands which we're all coming from today. I'm here on the beautiful lands of the Gadigal of the people of the Aurora Nation, and I'd like to pay my respects to the elders past, present and future. So we've got Dean Williams in the hot seat today. So Dean has over a 35-year career in precious metal exploration. He's worked with startup companies to major mining houses on 4 continents. So his specialty is district scale mapping with the integration of geochemistry, remote sensing and geophysical data. So I'm super excited to hear from him today about a solution to declining geologist field skills, which is based on his SGG discovery article called Capture Codes for Better Geology. So it's going to be a great session. I hope you all enjoy it. Please use the chat. You'll have the chance to jump off mute and we'll be opening up the floor at the end. And yes, thank you so much, Dean, for joining. It's wonderful having you.
Well, thank you, Jessica. I really appreciate you putting the time and effort to make this platform. I think it's a great resource for many people in many different disciplines. This talk is is on what I call capture codes, and it's to address a problem that a lot of people recognize, but is not well discussed or not very well discussed. And that is the decline in field skills. I'll go through some of the reasons why this, or my observations. I have a long-term perspective on this. I started my professional career in 1979, so I've seen a lot of changes in the industry. And some of the things that we did well before, we're not doing well today. And we'll discuss that. Then I'll go through my version of what a geologic mapping workflow should be and what I've used with great success. Then we'll get into lithic capture codes, then alteration capture codes, and then mineralization capture codes. I have capture codes for each one of these. Then I'll have some case studies showing how they're applied and what you can do with them. A few takeaways, a challenge, and then the references. There are many reasons why the suggested for the decline, universities not having field camps, and the way we do field geology or don't do it, etc. None of those I can really do anything about, but I can provide some of the insights that I've gained from mapping. Now, I'm not the world's best mapper. My field camp, I got a C because it was horrible. We were inside of a mass waste flow area in the rain, and nobody could figure out what was up or down. Or it was, I'm sure the TAs were quite amused that we could, if you stood back on the other side of the field, you would have seen that it was a mass waste area, and it would have been done in 5 minutes. But walking around in it, we were just totally lost. Silito warned us back in 1999 that field skills in the profession were deteriorating, were lessening. And now that's been 53 years. What we define as field skills is the ability to recognize, and that's where capture codes, that's their forte, is helping to recognize, map, interpret different kinds of rocks and structural disturbances in their juxtapositions. More advanced skills include construction of landforms and architecture of sedimentary basins and hydrothermal alteration. But my talk will be based mostly on simply recognizing what rocks you should be using as map units and why that's important. Now, over this period of time, we've had several trends where you have resolution on the y-axis and time on the x. Imagery. When I started, Landsats had pixels of 60 meters and the black and white were 90 meters. Today, you can get it down to 30 centimeters. So that's a 40,000 ratio increase in resolution. Plus, there's a lot more bands. Geochemistry, you've gone from penny weights to parts per trillion. Geophysics, well, when they started, they could find 80-meter tubes, that's submarines underwater. Now we can 3D visualize 2-meter fault displacements 2 kilometers underground. But geologic field skills have not kept pace. The consequences of that, according to Silito, are the potential for loss of information because unsupervised raw recruits are logging the core. And core is really the most expensive thing we have. It costs sometimes well over $100 per meter. And it's not, the information is, we're not gaining what we could just with a hand lens and a little bit of knowledge. Also, he concluded that he'd like to conclude that the discovery rate of major deposits has been coincidental with the decline in field skills. And this graph from 2016 bears that out with the gold and silver in the orange and green colors. The talk the other day on nickel it's the same thing. The last 20 years, no discoveries. So actually, we're supposed to be economic geology, but we've been quite uneconomic as of late. 65 billion spent looking for gold over this period of time to find $30 billion worth. That's a ratio of less than half. So that's not good. And that's nothing like sustainability. So lost in translation. Geologists spent a lot of time in the field and they had mentors. This is traditionally when I started. Geologists observed and described rocks daily. Every project had a library of rocks and alteration types and mineralization. Projects were mapped and drill sections constructed before they were drilled. That might sound pretty obvious, but not today. Geologists who logged the core, they also posted the values, interpreted the holes and in-between section, and wrote reports. A good format for those progress reports is what did you do and how did you do it? What was expected and what was actually discovered? What does it mean? And usually multiple working hypotheses because there's always variabilities and different possibilities. Then what we should do, why, and what can we reasonably expect? Contemporary mapping and logging is quite different. The least experienced geologists now log the core. They're forced to make subjective choices from predetermined lists of generic rock types. Now, this is a source of much of the inconsistency that we have. And those predetermined lists are usually done by people who've never been to the field. They're the computer guys that want a particular format for making their models. And logging is really, if the word itself is to record what you see. And if you're forced to do a multiple guess on what rock type it might be, including rocks that aren't even on the list, well, this is an obvious source for inconsistency. Geologists now rarely map, interpret data, or write reports. If it is done, if you do have mapping, it's usually by an outside consultant, and you can never gain all of the information that they do by mapping with merely a report and a map. And that information, it leaves the project. Rarely do you have a good rock library. You might have a few pieces of fancy core that's well mineralized, but you've already found the mineralization and everybody knows what that looks like. What we want to know is, what are the first indications of mineralization? Excuse me. What are the first sense of alteration that you're getting close? This is what you need because those shells are much larger than the actual mineralization. Map units are poorly defined, they're ambiguous, and often include the word undifferentiated. Geologists often don't have mentoring, they're unsupervised. And geophysics and geochemistry are done first, followed by drilling and the exclusion of mapping. This is often because many juniors don't feel like you can make a press release on, we have a great map. When in actuality, that would be a good thing to do a press release on, because it shows that you're understanding your mineralization, rather than running a geophysics that makes a pretty map and you drill the red blitz and you don't find anything. So you rotate the palette and then drill the new red bits. And also there's this concept that technology is a surrogate for a competent geologist. Well, that's enough of the negativity. This is the workflow that I have found useful in making maps. Now, if you have a project with a sandstone and a mafic lava on top of it, it's pretty simplistic to map that and know the two rocks. But working in the Patagonia and the Andes, that's not usually the case. I might have 7 different kinds of felsic pyroclastics that can be broken out as individual map units. And you need that to have a resolution to know where your structures are and the movement on those structures and the timing. So you need something more than the most simplistic checkbox that it's a rhyolite. So to me, I like this phrase, rocks are stock and trade. First, you have to do the identification, characterization of the map units. And this requires making and recording observations at multiple scales. These include at the outcrop. And you always tell a good geologist, he doesn't run up to the outcrop to begin with. He stands back and looks at the entire thing and sees the interesting bits. Then he comes up and breaks the rock and licks it. You got to get it wet to really see it, and then looks at it with a hand lens. Also, you need to map scale for inter-unit variability. I have an example of that in a minute. Then you have to determine the interrelationships between your map units. These obviously observed contacts, but you also have inferred and cutting relationships. Then you document each of your lithostratigraphic units. There's an example down below on what that looks like. And then you construct your stratigraphic column. Now, here's a variability within a single pyroclastic flow. Now, if it's a flow, it happens instantaneously. So it should be at least a map unit. But when you look at it, in A, you have wispy pumice. This comes from the non-welded and the glassy portion of the cross sections down in the lower left-hand corner. This is from McPhee, which if you do any work in volcanics, this is a must-have reference source. Then in the middle part where you have partial welding and vapor phase recrystallization, if you wonder what that means, it's those muralitic fiames. They look like granite. They've got actual crystals of quartz and feldspar in the fiame. And then the middle densely welded part that has been devitrified, you've destroyed these other textures, and then it's devitrified to create spherulites. So if you saw these 3 different rocks, you might think 3 different units, but no, they're one. Or you can use these for younging and actually get more data, and that'll be shown in a later example. You got to collect a lot of rocks. Every outcrop, every field station that you establish, you should pick up a rock. And before you write your name on it or the field station number on it, you should examine the rock. First, you have to beat on it quite a bit, make sure that you have fresh surfaces. But before that, you make sure that it's from there. You just don't pick up any rock on the ground. That could have come down from the hill, and it's not from there. So you have to make sure you are where the rock is. You have fresh surfaces. You mark it so that ideally you cut these with a diamond saw, and then you mark it twice with the field station. Because if the number gets rubbed off, and you only marked it once, then it's just a rock and you might as well throw it out because it's no more use. If it's hard to write on, put it in a plastic bag and label that. Once you have your library, you can start setting out your type samples of your units. And a particular note here is the center one in the bottom file, bottom row, where you have black and white lamination. Well, actually, that's transcurrent bedding. That's a surge deposit. A curious side note there. They didn't know how those things formed until they started having above ground nuclear blasts and very low density, very fast movement of from an explosion creates these textures. You should have one set of these in the office and another one in the core shed for reference. You should print up your descriptions, which I'll show you down below, and laminate those so you can also have them in the core shed, because everybody naming the same rock, the same thing, to have that consistency. Because if you don't, then your whole database becomes corrupted. And then it's good to, in your comments, list where you have your type localities. And if you have the hand samples and you print out a map with all your field stations, you can give a virtual tour of the project without leaving the core shed by just showing the rocks. All right. A rock name might be this quartz, biotite, lithic, ferric, etc. Rheomorphic, that's an interesting texture. I didn't know that one, but I ran across it and had to figure it out using McPhee. But that's a lot of verbiage to use all the time. So I created what I call a summary code. So once you have defined your units, you can define summary units. And these consist of a capital F, in this case for felsic, for the composition. The second letter is the rock type. And the third letter is the third rock that you found that you believe is a different unit, that is felsic and pyroclastic. The numbers have no correlation to the age of the units. They're merely coincidental the way you found them. If you started on the west side, they'd have different numbers than if you started on the east side. But I use these summary codes, as you'll see later, on maps, in reports. They're just much easier to utilize than the entire rock name. Following the maxim, separate in the field, combine in the office, because you can't do it the other way around. I take my rocks in the once I have starting building up a rock library, I will put them in piles of my different units, and I will look at them. Is there more variability between units or the rocks within the unit? Because if there's less variability between this rock and this unit and this rock and this unit, well, then you have to rethink. And this is not an easy process. It's an integral process. You keep going back to it and back to it. And by figuring out what rocks you really have, your lithostratigraphic column, often the final copy might have FP1, 3, 4, and 7, because FP2, 5, and 6 were combined with other units. You never know. You don't pick up the first rock and give it a name and keep going. It's an integral process. In the field, as I mentioned, you have to set up field stations. And this is to give spatial data for lithology observations, alteration, mineralization, structural observation measurements, field photos. If you take a field photo, I use the name of the field station as the file name. I put OC for outcrop if I'm looking at the outcrop, but always with something that's of scale. I use a geo tool, which I have the handle marked off in 10 centimeter intervals so that you have scale, because nobody knows how big those handles are. And if it's a view, well, then you give the middle of the photo, I give it a V, and then I give the azimuth so you know where it is. And from that data, you can, in GIS, you can set little arrows up and click on those arrows and have it linked to your photo. So you could give another tour looking at the map. What's that look like? What's that hillside look like? Click, and you take it, and it shows you. And this is useful not only for you in the office in the winter and you're trying to think about how that was, but for an engineer that wants to put a road through and then realizes, no, that's a swamp he wants to go through. And in one tragic a case, it was a photo I took, and later that day, a rock fell down the hill, and it was a fatality. And that photo was important in their investigation. You never know. And then, of course, all class of sampling, all done with field stations. Now, a field station can only have one type of lithology, because I usually work in spreadsheets. So if you have a contact and say there's a fault between them, you can have one station on the fault. So you multiple your data that you're collecting from each one. So you have the structural measurement and a lithology and alteration on the one, and then step over a few meters into the other rock to give the other rock code, so that you have both of them in the map, because you can't have two codes in the same spot. Then you transpose your field stations and bedrock outcrop. Traditionally, this is done on what we call clean copy. Excuse me. Where you'd have field sheets and you'd put them under Mylar and then trace them. More commonly, this is done into GIS programs today, and it's increasingly being done on screens. But my favorite and preferred way of doing it is you take air photos and you cut them and you print them together to make stereo sets, and you go to the field with those, because it's like walking around on a DEM. You have if you move your head back and forth, you might be able to pop that in. I can pop that into 3D. If you do, you'll see on the left-hand side, there's a mass wasting event came down that valley. You can see a lot of structures. And so you're in the field and you can see, well, that's interesting, or I want to go there, but oh, there's a cliff, I better go this way. So it's very useful. And to put the data on there, what I do is I take a pen where on a mechanical pencil, 0.3, there's a little needle on the eraser. I poke that through, and then on the back, I write down my field station. And on my field station codes go the first capital letter for the geologist, 2 digits for the year, and then 4 digits for the station. If you try less digits, then if you start with 1, 2, 3, it doesn't sort right in the computer. So start off with 4 digits. Then I come back at night, and then onto a georeferenced image, I heads up digitize my points. This gives you I use the GPS now, but when I first started, there were no GPSs. We used something called triangulation, which was a nightmare. That's where you take a compass and shoot 2 hills and cross the lines, and that's where you're supposed to be. The first GPSs weren't a whole lot better, because they were up to 1 kilometer off. Now they're quite accurate. But the problem with the GPS is it's mechanical. It's an instrument. If it drops, it's lost. Or once I just had one stop. And if it stops, you've lost the entire day's work, which is much more valuable than the GPS. So I have a field notebook, and I write down the coordinates of every single field station, because if you drop a notebook, it doesn't break. So you have a backup there. But I put the site, the points, I can put them in with the GPS data, and then I can manipulate them if they don't match what I see in the topography. And then today, with the high resolution imagery, much times it's better to do the outline of the outcrop in the office than actually in the field. So concentrate more on and taking key field stations, the little yellow squares of the field stations here, because you can actually tell better on those high resolution, the outcrop trace, than you can in the actual field. Here's a step that nobody thinks about, but if you don't do it, it could cause you problems. What you see in the color on the screen isn't necessarily what your plotter or printer is going to do. So I always plot out all the colors that my plotter will do. And then I will start selecting colors. You can see my summary codes there, and I pick out distinct colors, and but not too strong ones. My boss didn't like an explosion in a paint factory, he called it, if you put too strong of colors. And every unit has to have two colors. It has a darker tone to denote the outcrop, and a lighter tone to denote the interpreted solid geology between outcrops. So there, the outcrops are painted. The next step is to do that interpretation between the exposures. Your structures come in here, and you divide the structures into three ranks. Observed, they're measured, you can see them. They're projected, they're a bunch of lined up between observations, and it's pretty clear that the fault continues through there, or completely interpreted, running out through a field and there's no indication, but you think it's there. Then you take your juxtapositions and your stratigraphic displacements, and with these you create a structural model. And then using the integrated the geology and structural model, you create cross sections. So here's now the interpreted solid geology between my outcrops, and this is getting on to being a proper geologic map. You have your field stations, which they're not labeled here because of not to clutter the map too much, but the outcrops are labeled with my summary codes. And then you mark on your section line. And section lines, geologic sections, are kind of the acid test for how well you actually interpret and understand your geology. Now, you might note that in the lower portion, there are two different colors here of the outcrop, and that's an error. What it was, one's called FP8 and the other one's called FP1, and it turns out that FP8 was absorbed into FP1. It was just the lower portion of it. So the interpretation, the solid geology is correct, but that shows how these maps evolve. You don't go out and produce the map in one day. This is that section, and a huge amount of vertical relief can be interpreted because you have enough units. Now, there's one of my case studies deals with this same project area, and there was another map made of it that had a lot fewer units, and it was unable to make this kind of interpretation because you don't have the resolution. Now, here's a whole laundry list of things that your final printed map should have. And this is the list. If you ever published in a journal, these are the things you'd like to have on your map. I'm not going to discuss them now. They're pretty simple stuff. You can freeze the screen playing the video back. Now we'll get into the lithic codes. First, I'd like to share some endorsements. After writing the article, several people contacted me, and one of those was Professor Dan Wood, and who in Australia, some of you may know. And what he said was it had a number of advantages, the capture codes, over what he used at Cadia Hill. He was impressed with the hydrothermal alteration modes of occurrence, and he noted that it covers the total complete range of lithologies. And he also said it was intuitive, which is nice, and which makes the logger's life easy. The other endorsement is by Stefan Enders, who is the head of the Colorado School of Mines. And I'm particularly proud of this because he said that he liked the codes enough that he's using it as a reference for his in his curriculum. One of my peer reviewers, I think kind of tongue-in-cheek, described the codes as producing unique codes that represent every permutation of rock types and textures imaginable. And actually, he's dead on. If you're going to be able to describe any rock on planet Earth, you need to be pretty variable. when I started these codes, the reason why these codes were created was I was in charge some time back on mapping a large project in the Andes. A lot of rock types, a lot of alteration, and I had a large group of geologists. And to begin with, it was impossible to produce any coherent data. So the system was designed so that no matter who was making the observation, they would make the same observation. And the system was wrung out of any subjectivity. It's all objectivity. Now, this is capture codes. They're not rock codes at all. They're quite different. I'll explain that further. So how do you get everybody on the same page? I follow the maxim, first observe, then interpret. So here's a triangle of how you develop your map units. The first phase is the observational phase, where you look at the outcrop scale, you break rocks. You have to break rocks. The weathered outside, you can't tell anything. And that's why a lot of remote sensing doesn't work very well, because a millionth of a millimeter oxide on the outside changes what's being reflected back to space. You need to break the rocks open. You need to look at them with your hand lens. You need to collect hand samples. The next phase is the analysis. You take these observations and you combine them, you massage them, and you match them up with your geologic knowledge to get to the interpretive phase, where you define your map units and define codes. Now, the standard practice is you put rock and logging codes at the initial stage of the observation. These are transcribed into the database, and there they are. They're in the database. They're unauditable because there's no backup data. If there is a description in your column that says comments, it's useless, because today, if you can't take a mouse and with 3 clicks, spin your data in 3D, it's not going to be used. And if you have 200,000 meters, each meter with a description, that's wasted time and space, because nobody's ever going to look at it. The capture codes, versely, you capture observations. They are objective, empirical data. They are not interpreted what it might be. It is what it is, so that you or I or anyone that sees it will see the same thing. Then you put that into the database, and the format, these codes, their architecture is a format that is sufficiently compact that it can easily fit into a data sheet. You can easily use a digital data collecting device to collect them. You can separate them out in individual columns, and then you can query them or sort them on singular or multivariate features. Then you come up with your summary code for your map units. Now those, instead of just picking a rhyolite and that's it, it's rhyolite, but somebody else called the same thing a dacite. How do you tell the difference? You can't. You have to go back to the field. With these, you can go back down to the lithic codes and see how much quartz eyes, what size was the quartz eyes? Were the quartz eyes embayed? Were they rounded? Were they anhedral? All of those different characteristics, details can be captured with lithic codes. The fields in the lithic codes, there's yellow headers across the top of the sheet, and those are your 7 basic lithologies: pyroclastics, lavas, and subvolcanics. Now, these 2 are joined because if I came across a small outcrop and it was porphyritic with an aphanitic matrix, I don't know if that was a flow or a high-level dike. So to take away that subjectivity, I combine these. Clastic sediments, chemical sediments, fragmental rocks, which can be a real nightmare. Intrusive rocks, well, those are wholly crystalline. They're easy enough to tell those because they're wholly crystalline, opposed to the subvolcanics or the lavas. And then metamorphics, which are also can be tricky, but I use strictly textures. I don't try to guess what the rock might have been. Then there are gray headers. fields where the choices are all mutually exclusive. You can only choose one because it can't be two of them at the same time. Plus, the architecture of the code is such that it only allows for one choice. Because if you start putting in different choices, you've corrupted the format and it becomes useless. Then there are blue headers. Here, you're encouraged to make as many choices as you can. And this is where you get a lot more specific information and key characteristics in which to tell different rock units apart. And these can be user defined. Excuse me. So there's only so much space on the codes, so you can only put in so many minerals or textures or components. But usually it's only a handful that are critical to your project. So the first stage of mapping is going out and seeing what variability you have, adjust the capture codes to reflect that. And the longer you work, the more you've seen what there is to be seen. And so every time I start a new project, I may modify the codes. This is what they actually look like. There's each column is a different rock type. You can see the gray headers, then the blue headers. Now that's all very confusing, but it's small enough you can print it out or print just the columns you need, because most projects don't have all of these on it. Now, why don't I use standard rock types like rhyolite, dacite? Well, because to classify those, they're done by 4-acid digest and plotting the silica against the alkaline. And I can't do that. I can't tell the difference with a hand lens. And if it's altered, even less so. Because as I mentioned before, if you force these subjective choices, you're only going to cause inconsistency. And as the rock becomes more and altered, and I'll show you a photo of what rock does when it alters, those inconsistencies are going to be worse. I worked on one project where there was a quartz diorite, and when it was black and fresh, you broke it, you couldn't see the quartz because they were clear. But when it became advanced argillic and all white and soft, the quartz stuck out. So people would change the name of the rock depending on the alteration. And that's, you just can't do that. You can't create a coherent geologic map if you change the name of the rock just because of the alteration. So to reduce this, I only use 4 compositions. And ultramafics, well, in Australia, you've got a lot of those, but in Canada, maybe, but a lot of other places, you only have 3, the felsic, the intermediate, and mafic. Because I believe it's better to be correct, general, correct, and consistent than try to be specific and run the risk of being both inconsistent and incorrect. Now, as an aid to how to choose these, felsic, it's oversaturated with silica, and so you see a lot of notable free quartz. The intermediate, much less quartz, maybe a little, but not very much, and not much feldspathoids. Mafic, there's absolutely no quartz, and you've got abundant feldspathoids. The ultramafic, you have an abundance of mafic minerals like olivine or pyroxene. So I'm going to go through each one of the types of rocks and code it so you can see how this functions. So pyroclastic, down below there, I'm building up this capture code. Capital P for pyroclastic. Then it's a felsic. And then it's a tuff. The tuff is based on these tertiary diagrams. You just don't, if it has 1 lapilli, you don't call it a lapilli tuff. It has to have over 25%. And actually, that's quite a bit. You see a lot more tuffs than lapilli tuffs. And some of these things are marked in the macro photo there with a few of the textures labeled. This actual rock with the J is an interesting one. That is a juvenile class. You can tell the juvenile class because the phenocrysts are anhedral. because in normal tuffs, as they exit the volcano, the mechanical and the the thermal shock breaks them. This is all explained very well in McPhee. That's where I learned a lot of this information. But in the juvenile class, that didn't happen, so they're still anhedral. That's also the way you can tell if you have an extremely densely welded tuff as opposed to a lava. The lava will have all one size or maybe two size phenocryst, and they'll all be nicely crystalline, where in the pyroclastic, they'll be broken. So then we move on to a blue section where you can select more than one. So this is crystal fragments, eutaxitic, Friami, juvenile, moderately welded. And then in the minerals, instead of going quartz, QTZ, well, that's a waste of space because the Q tells me what I already got, quartz. In these systems, in 3 digits, not only do you have what mineral it is, you have its size range and you have its percentile. So we have quartz or biotite in this case. It's fine because it's less than a millimeter. These are standard sizes. And then we have trace amounts. The percentiles are in brackets where it's easier to estimate what those are. And you should always be using those little cheat sheets with percentiles on them. So here we have coded this rock, this quartz biotite, feldspar, ferric, Fiami, and juvenile clast-bearing eutaxitic moderately welded felsic tuff containing blah, 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 blah. All of that, you put down a summary term like FP1, and this is the capture code for it. So, and why is it important to have that much detail? Well, here, all 4 of these pictures are the same rock type, going in from propylitic to argillic to advanced argillic to residual silica. Now, you have to map all of these as the same rock type because you can't change it because the alteration changes. Geologic maps don't work like that. So, but you always, it's good practice to map from outside the district where you see everything fresh and watch things change as you go into the center. If you jump into the center of this where it's the residual silica, then it would be very difficult to figure things out. You have to go back and forth. This is on a high sulfidation project. And if you ever have one of those, I suggest you make a matrix with rock types on one side and alteration styles of alteration on the other. And this way you can see how each rock changes based on the kind of alteration. Now the alteration is based on what minerals you have. Corbett does a very good description of argillic and advanced argillic, etc., by what minerals you have. And I'll discuss that more in the alteration codes. But by knowing your rocks well enough, you can even look at this very altered rock and know which one of your map units it belongs to. So here's subvolcanic, felsic, aphanitic. These are gray headers, so it can't be felsic intermediate. You can't hyphenate it. It's aphanitic or it's fine grain. It's glassy. It's one of those. You can't mix those. In that way, you know exactly in the code what it means. Then you start with its porphyritic, zoned feldspars, glominophoric. All of these textures tell you a lot about the magma and the history of that, and they help give you a fingerprint on each one of your units so you can start distinguishing them. It has quartzites that are spherical, which means they were being reabsorbed. And then on the minerals, you got the quartz. It's coarse. You always choose the largest crystals well, at least in pyroclastics. In lavas, you might have bimodal or single modal. But in pyroclastics, you always go for the largest that you can see because, originally they were at least that large. One project, obviously it was coming from a granite melt because I had a quartz phenocryst that was 9 millimeters. And I think granite's about one only kind of rock that kind of has that kind of large scale or something like that. But granite, again, that's a name. I use felsic. and it's a minor amount in this case of the quartz minerals. So here again, you have a descriptive name, and then you have the corresponding capture code. Classic sediments. Again, you have gray headers. It's one of those. You can't be more than one of those. This is a muddy sandstone. And in this case, the roundness of the grains, you can't tell. They're too fine. You can see the hatch marks on the right-hand side are millimeters. They're not centimeters, millimeters. So that's quite fine. And you just can't tell. So if you can't tell, you state you can't tell. Then it's normally bedded. It's laminated. It's fine coarse interbedded. And there's some soil and lode marks. And it's moderately sorted. Then you move over to color. In pyroclastics, color doesn't give you much advantage. And that's why I don't use it, because the colors can change so easily. And sediments, color has a lot more primary importance. So that's why colors are used in the classic sediments. White. And so there's the code, and there's the tertiary diagram showing why I took muddy sandstone as opposed to any of those other types of classic sediments. Chemical sediments, it's a Q. The type, this is a siliceous sinter. It's laminated, and it has vugs, and it has 3 different colors to it. So there's the very short code for that sinter. Now, fragmental rocks are quite difficult, and I had some suggestions by one of my editors for the paper, which I incorporated in this. So there's a lot more gray headers in this zone. So the fragmental rock, it's class supported with cement. You can see that it's class supported because everything, all of those class are touching each other. They're not being floating in a matrix. The composition, they're all heterolithic. Now I've marked the E there, that little band, that might look like a carbonate out of a vein, but actually in this case, it's a stromatolite that was caught up in this hydrothermal breccia. They're poorly rounded because not everything's rounded. They're rotated, obviously. Here you take the modal class. What's the average size in there? Then textures, here it's a blue, so you can put more textures. The matrix, this is hydrothermal minerals, and how much of that matrix are sediment. So there's the code, there's the description. Intrusive rocks, felsic, it's porphyritic. This is a granite, but it's a porphyritic granite. It's medium ground mass. It's graphitic, little g there. And biotite, medium size and minor amounts. So there's the description, and there's the capture code. Metamorphics. Here you've divided the textures into 3 parts, A, B, and C. The strongly foliated, weakly foliated, or non or poorly foliated. So you can only take one of those. And in this case, it's a metamorphic, it's strongly foliated, and under that, it's a schist. And then you have garnet. These minerals are specifically selected because they're metamorphic minerals. There's a size range, and there's the how much you have. This is a very nice sample in my collection from Alaska, famous site. I forget it right now, but some very nice twin garnets. Okay, alteration codes. These are much simpler. They have 4 parts. There's the alteration mineral species, the mode of occurrence, the crystallinity, and the pervasiveness. Each field is separated by a capital letter. The mineral and the mode of occurrence can be user defined. So whatever your project has that's important, you can define these yourself. I also add in the mineral species U for unspecified, because many of these fine white powdery minerals, you don't know what they are, and you'd only be guessing. If you lick it and it sticks, and it might be alunite, maybe not. So do your spectral analysis and then update your codes. Now, the important thing here is that you only code one mineral species and in one mode of occurrence at a time. So if you had alunite replacing phenocryst and you had alunite infilling fractures, that would produce two codes. This protocol enables you to collect data in far greater resolution and synthesize it and analyze it. This will let you play what if games. So if you can say where do I have barite growing in cavities, and associate that with maybe your gold value. You can look at those clouds in 3D and get relationships. You can do a lot more into the data. So coding, it's chlorite, replacing just phenocryst. It's microcrystalline, and it's moderate as opposed to weak or strong. These are reduced down so that you increased your probability of consistency between people. The picture there, I apologize, it's not very clear, but the chlorite is replacing the biotite, and it's also infilling microfractures, which you really can't see there. So the first code is a chlorite replacing just the phenos, and then the chlorite with fracture filling. Now, the crystallinity is very important because if you do, Corbett describes 5 different kinds of alunite in a high sulfidation system. And depending on how crystalline it is, where you are in the system, if it's a porcelain or if it's coarse blades that are 3-4 centimeters long, it depends on where you are in the system. And it's all about understanding, using the generic models and using what you're observing to figure out where you are and where the mineralization might be to guide you. Mineralization codes, the first 3 parts, excuse me, are identical to the alteration codes. The fourth, instead of propensity, it's percent range, and that's the entire rock. Again, the same, one mineral species, one mode of occurrence. Here, we're looking at galena. It's the breccia matrix. It's fine crystalline, and there's 7 to 15% in the rock. Now, if there were some phenocrysts that were also being replaced by galena, that would be another code. So there's the code, and you can have multiple codes for the same rock for every mineral species and for every mode of occurrence. So here's some case studies on using these codes. Here's some examples. I went to a project and they had the orange were an intrusive rock, and the purple sea out there was what they called undifferentiated pyroclastics. And they believed that the intrusives were striking nearly north-south. Well, I looked at the rocks with these codes and I was able to divide them up. Those rocks in blue, 3 shades of blue, well, those are the ones that I showed you above, where you have 3 different parts, the lower, middle, and upper part of one pyroclastic flow. The middle of the green colored ones is the one that we just did the pyroclastic test on. So utilizing these, I produced a map that looked like this, a little bit different. And immediately what jumps out to you is, well, it looks like there's a fault there, and it looks like it's a parent strike slip displacement. And that was the interpretation that I gave. I printed it, took a pair of scissors, cut it, and slit it. And like my friend Greg Corbett says, magic. It just came together. And what you can see here is now the intrusive rocks look like they're lined up on a northeast structure crossing with northwest structures. So you can do, and all of those other structures that are in there with showing which side's relative down to the other, you have a whole structural model based on greater resolution in your mapping. And that's what it's all about. You can't go out and just measure a bunch of faults and come up with a complete or optimal structural model, because you need those other things of the geology. If you have a fault and you call either side the same thing, you don't know the timing or magnitude of the movement. But if you can have greater resolution, then you can get greater resolution in all of your interpretations. And all the interpretations are to better understand your geology. And that's why geologists are hired, and that's why we make maps. It's to increase your understanding, your geologic understanding of the project, because that reduces risk. Here's another study. In 2003, I mapped a project just using hand lens and the codes and developed 22 individual map units. Sometime later, a student doing a master's thesis came in, and he tried to duplicate my rocks by only doing thin sections. He sent off 60 rocks. They all came back as having shards and phenocrysts, and he couldn't make heads or tails. So he reduced them down to these units. And if you notice, unit 4 and unit 2 are actually the same description. And you remember I mentioned the basal surge? Well, that was his unit 3. It's not a sediment. So actually that's part of a pyroclastic fragmental. So you can reduce in his entire 2, 3, and 4 to actually 1 of undifferentiated pyroclastics. And his lower green unit, well, he didn't do his library search, because he would have found that the project was sitting on the side of a continental scale graben with at least 2,000 meters of displacement. And what he was looking at lower elevations was actually corresponding to what I have at the top of my my main stratigraphic column there of that volcanic sediments. So not only, but he used a lot of technology to do this, and his stated objective was to have a more refined stratigraphic column, but I don't think he met that. Now, talking about how to document it, every time I do a map, I have an appendix, and each appendix, within the appendix, I have a page dedicated to each rock unit with a macro shot and oftentimes a outcrop shot, especially when they're nice like this, forming those columnar joints. Now, this is your rheomorphic texture. It's when a pyroclastic is placed with enough heat and lithostatic pressure and on a slope that it begins to flow. And it's easily, you could think that was flow banding, which it is, but it's not in a lava, it's in a pyroclastic. So there's a detailed descriptive name. Then there's a full description, a paragraph talking about components, textures, and that it forms columns, et cetera, et cetera. Then you have the distribution. Where in your study area is it exposed, and where do you think it lies underground? And then the field relationship. What does it lie over? What lies over it? And what cuts it? And if you can, if it's pre-syn or post-mineralization. So if you can't fill out a sheet on each one of your map units to this detail, maybe you don't know your map units well enough. This student came up with this novel low sulfidation model where the low sulfidation quartz veins were emulating out of what he called the rhyolite dome. But I was mapping. This is why I say the outcrop is the ultimate court of appeals. I found this outcrop. This, as Corbett would say, it was magic. The arrow points to a class of quartz vein. So what is actually happened here, you had the emplacement of the quartz veins, differential block faulting and erosion, which was shown in the cross section, uplifted that portion uphill from here, to the point where several hundred meters of material was eroded, exposing the vein. The vein rubble was on the ground. There was enough topography to create a mass waste down the hill, incorporating that quartz. That was preserved by being covered by subsequent pyroclastic post mineral age. And then it was lithified, and then it was cut by felsic intrusives, which correspond to his rhyolite dome. So by two sets of cross-cutting relationships of the veins and the dike, there's no way the veins were sourced from the felsic. Okay, almost done. Some takeaways. Observe first, then interpret. Capture codes are designed to record those detailed observations. Divide in the field, combine in the office. The recognition and characterization of lithostatic units is a fundamental into producing a coherent geologic map. Capture codes can help you do that. Capture codes can improve the geologist's field skills by forcing them to look and providing them a template, an objective template, systematic, how to look at rocks. And in fact, in logging, this could speed up the whole process. And really, I don't like the idea that these are logging codes or these are mapping codes. They're all the same rocks. If you're underground, if you're looking at a core is nothing more than high percent outcrop exposure. That's what tunnels are, 100% exposure. Also, the capture codes, because they're objective data, you can establish QA/QC protocols so that if two people, one called it an andesite and the other called it a rhyolite, and you don't know, you can go back to the capture codes. Did it have quartz? No, it didn't. Okay, then it looks like the andesite was right. So you can maintain consistency. And since we QA/QC everything, we don't do it lithology, and which seems weird because that's what we're all about. Now, I'm a little bit jaded, but the majority of rock coding systems are basically subjective labels with no means of verification, whereas capture codes are empirical observations. Now, a bit of a challenge. If you think capture codes are just way too much work, conduct a geologic audit. Collect 10 samples. This is the boss man coming out, taking 10 samples from across the project area, different kinds, label them 1 to 10 without saying where they're from, because people map Mary's Tuff because it's at Mary's Hill and Juan's Tuff because it's at Juan's Hill. No, that's not the way you map. You map by what you're looking at, not from where it came from. And so have every geologist label code in your coding the unit, alteration, and mineralization individually. Now, a lot of geologists might be a bit put off by that, so you might do it in some fashion where it's anonymous, because you just want to know if your people are consistent or not. You don't want to, it would cause problems if geologist A, Y, or Z was called out and said, you know, you're not what you're doing. So you just want to know, are you correlative or not? If you're highly correlative, then congratulations. If you're not, perhaps you could consider using capture codes. This, of course, has a caveat that your codes themselves are unambiguously defined. And these are the reference that I've used in this talk. Thank you.